we must look at reflexivity for that set. We must look at symmetric, and we must look at transitive. I'm sure we know this. How to define a relation. So we can say that R is called a relation if it is either one of these, right? But then if it's an equivalent relations, it must be the three of them. So it can be, for a relation, we can have reflexivity, we can have symmetric, antisymmetric, and transitivity. So any of these, if any of these is satisfied, then R is called a relation. So when we come to the, I've included some of the examples. I think I've included two of them that we're going to be looking at based on such relations. So when we come to a relation, we're saying that a relation R from a set A to a set B is a subset of the Cartesian product A cross B, such that a collection of ordered pairs X, Y, where X is an element of A and Y is an element of B. So what I'm saying here is that if we say this, we say that R such that R will be a relation such that we can have something like this. We can have A cross B going to something, a certain set, or we can have A to B such that this will contain a Cartesian product, right? So now, let me do this. So when we come in this case, we are saying that if we're given an example here, that we let A be 1, 3, the set 1, 3, then we let B be the set 2, 3, and 4. So for possible relations, we can take possible relations. What we're saying about possible relations, that we can formulate any type of relations from this, right? We can have 1, 1, 4, we can have 1, 2, we can have 1, 3, we can have 3, 4. So any kind of relations can be formulated from this. So sometimes they'll give you this type of a format, then they ask you, is this a relation symmetric? Is it reflexive? Is it antisymmetric? Is it transitive? So they're just gonna ask you, is this a relation? You say, right. So, or they ask you, is this an equivalence relation? Which is, you have to check the relations one by one. You check R1, is it an equivalence relation? You check R2, is it an equivalence relation? But what I want us to focus on here is how to find A cross B. Alright. The question is, how do we find A cross B? So for us to find A cross B, we see that every time if I have to cross or I have to formulate a relation, I must have these curly brackets outside, then have these open brackets for every set that I pick, for every ordered pair of set that I pick, just like in the definition. We say that the definition said that we must take a collection of ordered pairs. So in this case, I'm going to take it them like this. I take 1, 2. I take 1, 2. I take 1, 3. So I'm just gonna take 1 and 2, 1 and 3, 1 and 4. Right. Then I take 1 and 3. They must be ordered. You see, right? They must be in order. Then now I come to 3, take 3, 2, 3, 3. And then I take 3, 4. You see, right? Now, if now I need to take what we call BA. If now I need to take BA, B cross A, it means that I'm going to start taking from here, from B to A. I take 2, 1, 2, 3. You see, right? I take 2, 1. Then I take 2, 3. Then I come to the second set. Take 3, 1, 3, 3, 3. So I take 3, 1, take 3, 3. And then I take 4, 1, Check for 3. Check for 3. So once we check this, the next question that we can ask ourselves is A cross B equals to B cross A? Who can tell me, are these two equal? Is A cross B equals to B cross A? Anyone who can give us an answer, you can just say any answer, yes or no. Are they equal? It's worth trying, Is A cross B equals to B cross A? Is A cross B equals to B cross A? Okay, so what is the thinking about that solution, right? We'll move to the next part. So now we come to the types of relations, right? Make sure you can also give that solution in the group, or I don't know, you'll see. If we come to the types of relations, then we have properties of relations. As I said, we have 4 properties, which for R to be a relation, it must meet at least one of these 4, right? So R can be reflexive, it can be symmetric, it can be antisymmetric, or it can be transitive. So they go in order. Always, if you know that reflexive comes first, symmetric comes second, antisymmetric actually usually goes with symmetric, but then you just add some few things. You're just gonna add some implication there such that A is equal to B. Then for transitive, it includes 3 elements. So when you come to reflexive, right, reflexive includes an element which is A. A should be related to itself. You see, right? One element should be related to itself. Like for an example, when we have 3, 3, you see, right? Then such should be related to itself. So we are saying that for a reflexive, we are saying that for all A element of A. So first, when you define any of these properties, you must state their set, that this is taken from which set, and then it will be related if this and this happens. So here we are saying that if we take the ordered pair AA, which is an element of R, then this is a reflexive. We say that. Then for symmetric is usually the original question that they give you. Usually they'll give you that the ordered AB is an element of R, meaning that A is related to B. So yourself, you must come and show that B is related to A. You say, right? So when you come to antisymmetric, automatically we assume, we remember this from this one, what's this topic, mathematical logic, right? We remember this from mathematical logic, methods of proofs, that this one usually it's called a conditional statement. You see, right? Once you have an implication, this is called the conditional statement or the statement. This is the hypothesis, and this is the conclusion. So in other words, when you come to antisymmetric, here you just assume that this is true. You don't have to prove it. Even if this had failed, even if we checked that, okay, this relation is not symmetric, then when we come to antisymmetric, we must just assume that this part is true. You said we must just assume that there is a symmetry. Then we come to show that A is equal to B. Showing that A is equal to B is quite simple. You'll see when we come to some examples there. Then we come to transitive. We have for all A, B, C. So for transitive, we're going to take three elements. We show that if A is related to B and B is related to C, then A must be related to C. It can be through some sort of association. Sometimes it can be equality. It depends, right, on what type of this sign they gave you, the symbol they give you. So when we come here first, we take that for all A, B, C, element of A, AB is related to R. You see right now? So it's an element of R. And then we're saying that, remember, this simply means that A is related to B. And this simply means that B is related to C. You see, right? Same as this one, simply means that A is related to A. You see, right? So something like that. So this is what you must know. So if A is related to B and B is related to C, then it means that A must be related to C. That's by transitivity. So if we know transitivity, it's going to be simple for us to work around this. So now if you have any question, you can stop me, right? If you have any question, let me see. If you have any question, you can stop me. So remember I said that for an equivalence relation, we have a definition to say that a relation R on a set A is an equivalence relation if it is reflexive, symmetric, and transitive. So here we don't include the part of antisymmetric. Usually antisymmetric is not discussed the most. So now when we come here, we have one problem that they say we must show that R4 is an equivalence relation. But let's start with this problem here. Let's start with this one. So this one. Yeah. They say show that R on Z defined by R related, X related to Y. Right? If X is equal to Y, then this is an equivalence relation. So in other words, this is the same thing as saying that let me put a pen. The same thing as saying that if we take X, Y, the ordered pair XY, which is an element of R, then X will be equal to Y. Right? So now what we're going to do first, we're going to check for reflexive. Remember, we always check for reflexive first. We take one element. I'm going to take one element here. So what I'm going to say, for me to show that X is related to X for all X element of Z, since X is equal to Y, when X is equal to X, it follows that X is related to X. So what I'm going to do here, this is how you're going to solve it, right? So yeah, I wrote you this statement so that you can read through. So what I'm going to do here, if you want to solve for reflexive, right? For reflexive, you can just write reflexive. Every time you solve for reflexive, you can just write the reflexive and then you underline just to make sure that the lecturer knows what part you're solving, right? Then you say for all, now again here we're having XY, so I'm going to take X only. For X element of, this is defined under what? Integers. Our set now is an integer, so I'm going to take for all X element of an integer. And then I say that, now I'm going to say this. So I say that X will be equal to what? X. You see right now? According to the definition, if I take X element of Z, then X will be an element of X. So it follows. So it follows that X is an element of R. You see, right? So now we have shown that R is reflexive. Thus, R is reflexive. Or you can write, instead of writing this one, you can write this one. You see, right? These are two and one and the same thing. So now we come to showing that this is symmetric. So for us, if we want to show that if this, then this, you see, that's what you must show for symmetric, right? So we must show that this is A and this is that. Then we're going to suppose that X is related to Y, because that's the assumption that we must take. That's the original statement we're given. We must suppose that X is related to Y. Then we show that Y is related to X. How are we going to show that? So let's come. We suppose, let's do this. We suppose that X is related to Y. And for X to be related to Y there, the definition says that when X is related to Y, X is equal to Y. You see right now? And from here, I'm going to imply I take this to the other side. I take them to the other side. I apply commutativity. Alright. And then I divide both sides by negative. I'm going to have Y is equal to X. So I've shown now that Y is related to X. Thus, R is symmetric. So the reason why I didn't write them like this is because I read these things using a code, you see. So having to code down these type of steps, it takes a lot of time, and I was doing other things, so I had to write them like this. Then I knew that I was going to explain them here. So now we have shown that this is symmetric. You said, right, for symmetric, always show that this thing commutes. So you must apply commutativity, you see, show that it commutes. So if it doesn't commute, then, and when it commutes, the sign must remain the same. Then it means that if it doesn't, then no, it won't. So now we must show transitivity. We must take three elements first. So we must take three elements. Yeah, here I didn't take those elements. I should have said first for all X, Y element of Z. I suppose this. So now I'm going to take three elements here for transitivity. Say for all X, Y, Z element of Z. Now, here what we are given, here for transitivity, we must suppose these two statements. Then we show that X is related to Z. You see, right? We must show this, then we show that X is related to Z. So I'm going to suppose that X is related to Y, which implies that X is equal to Y, and also Y is related to Z, which implies that Y is equal to Z. The aim is to show that X is related to Z. You see, right? And here, this, what we know here is that if X is equal to Y and Y is equal to Z, you see, right? It follows that X will be equal to Z, because I can just combine these two, then X will be equal to Z. You see right now, which implies that X is related to Z. We agree there right now. Thus, R is transitive. So, if the relation R meets all these properties, if the relation R meets the property of reflexive, symmetric, and transitive, then we know for sure that this is a symmetric, this is an equivalence relation. We know that this is an equivalence relation. That's why for a conclusion here, we must come that to say that since R is a reflexive, symmetric, and transitive, then R on Z defined by this is an equivalence relation. We say, right, then this will be our conclusion. So we know that this then is an equivalence relation. So now, yeah, so this is just the summary of the two examples. Then now we go back to the first one. If you have a question, remember to stop and ask me, because if I'm the one asking the questions, you don't reply, right? So now we come here to the problem, right? The first problem, we say that we must show that this R4 is an equivalence relation. Then the problem says that we show that R4 is both reflexive, symmetric, and transitive. Hence, R4 is an equivalence relation. So they'll just come and say, show that this is an equivalence relation, right? Then now the context says this, must let R4 be a relation of from R to R defined by this. So it's defined by X minus 4 minus Y. If X minus Y is divisible or multiple of 10, then it's a written like this. Sometimes they won't tell you that it's a written like this. You must just know that when they say that is divisible by, or is a divisible of 10, they're trying to say that you must say that X minus Y is equals to 10K. You say, right? So 4, now you define what is K. K is an element of an integer. So you must know this statement by heart. All right. So now, this is how we define a reflexive. We must first take an ordered pair such that we show the formula of the ordered pair. Then we give the definition that it must arrive to. Then the K must be some sort of an element of an integer. So you'll see this when we come to the second lecture, which we're going to have after here. So now for us to show this, first we must show reflexive, right? For reflexive, we're going to come and say this is moving from R to R. So first we must show that X is related to itself. Remember, always reflexivity, we must show that X is related to itself for all X element of R. So we're taking from R, right? So here, so here we have X minus X. So this one, according to the definition, remember the definition says that X minus Y. If we take the ordered pair XY, in other words, when X is related to Y, you said it. But if I take the ordered pair XX, it means that this will be X minus X, because now the X has taken the space of Y. You said right. And this will be X minus X, which is equal to 0. So now from here, when we check 0, 0 is still a divisible of 10, or it's still a divisible of 10. I can be able to divide this by 10. You see, right? So this is still a divisible of 10. So that's why when we come here, we say that since 0 is equal to 10 times 0, I can divide here by 10. The 10 can go. Then I'm left with that 0. You see, right? So, and 0 is an element of an integer. So now we're saying that X minus X is divisible by 10. Thus, X is related to X for all the X element of R. So R4 is reflexive. Now, in most cases, what I'm going to say here right now, I want you to use the structure that I'm using on this one here. So first, what you're going to say is this. We are going to say that for all X element of R, you take the definition is equal to 0. Then after having that, you're going to state this what I've written here right now. Since 0 is equal to 10 times 0, and obviously it means that check from the definition above, it said that we must have this 10 times K, and K should be an element of an integer. You see right now. So we managed to change this to that definition. This should be an element of an integer, and this should be 10. So in this case, we know that 0 is an element of an integer. Hence, x minus x is divisible by 10, or is a multiple of 10. Thus, x is related to x, which is an element of R4. And this was R4. Right. So now we can give this to say, so R4 is reflexive. Now, when we come to this one now, we're saying that now we must show symmetric. For us to show symmetric, guys, remember we're going to say for all xy, element of, now let me say this one, they had said that it's moving from, did I say R for element of, yeah, it's R, just R, this one. It's moving from R to R. I must put it to show that this one is a set, not a relation. I must put it like this, show that this is a set. It's moving from R to R. Yeah, show that this is a set. So this is moving. We're taking this from R. Take xy from R. And then we suppose, remember for symmetric always we suppose the hypothesis, we suppose that x R4, y, in other words x is related to y. Then this implies, if this, according to the definition, they say that this is the case if x minus y is equal to 10k for some k element of an integer. You see right now. Then now we apply commutativity. Remember I said that we must commute. You see, you commute between these two. So since they're on the same side, we're just going to commute it there on the same side. Then now I must factor out. It means that I must show that y minus x is an element of that. So I'm going to have y minus x. I factor out a negative. Let me put the negative first there, because for it to make sense. And then from here, we're going to imply that now we know that y minus x, so the negative should be taken by k. If I divide both sides by negative, so the negative should be taken by k. So since this is the case, you see even here the negative was taken by k. Since this is the case, then I've arrived here, you see right now, where we have this. Now we're going to say, since this is an element of what? An integer. Alright. Hence, this whole statement is divisible by 10. Hence, this is divisible by 10. You see, thus, y is related to x, which is an element of R4. So, R4 is symmetric. So, that will be the case there. Now, any question? If you have a question. If not, we proceed. So, now we're done to show that this is symmetric. It means that now we can go to transitivity. Transitivity, we must first have for all x, y, z, we're going to have an element. These we're taking them from R, remember? And then we suppose, remember on transitivity we suppose two things. We suppose that x is related to y, which implies, according to the definition, that x minus y is equal to 10k. And also, now we suppose that y is related to z, which this implies that y minus z is equal to 10. We can't choose the same constant, so this time we must choose h. For some kh element of an integer. You see right now. So now since we have this, we have supposed this. Now for us to show this transitivity, right, we have this. We must show that this is transitive. Then what I can do here, I can make one thing subject to the formula here. Let me see what I can make. Or if I don't want to make anything subject to the formula, with transitivity, it allows us to do this. Let me show you. It allows us to come and say x minus z. I kind of want to show that x minus z is what is transitive, right? What I can do, I can add these two to find that. Or yeah, I can add them because this is negative, this is positive, they're going to cancel. Or I start here of saying x minus z is equals to, then I have this x minus, I add y in between. You see, right? You can add y in that format. And then this means that we know x minus y is 10k plus y minus z is 10h. Then here we're going to have 10k plus h. So we're able to put it in this format. Hence, now this k plus h is an element of an integer. And then this will mean that this equals to 10k plus h is divisible by 10, or is a multiple of 10. Let's check. Then we have that. We can also start here. We add our y in the form of 0 minus y plus y. Then, after that, we factor out our 10 here, right? Because we know that this is equal to 10k plus 10h. We factor out our 10. Then we state that k plus h is an element of an integer. Reason being is because k is an element of an integer, h is an element of an integer. So when we add the two integers, we're still going to get an integer. So we have this. Thus, we can state that x minus z equals to 10 plus kh is your 10 into k plus h is divisible by 10. Hence x is related to z through R4. Hence R4 is transitive. So since R4 is transitive, it is symmetric and reflexive. This means that this is an equivalence relation. You see right now? Then we're done. Any question on this? Any question, guys? So if you don't have any question, it's fine. So I'm going to do this, right? So yeah, this is the last part of this problem. So what we're going to do now, this will be the last part that we're doing. Then I'm going to stop the session. So I'll send the problems that you're supposed to do, right? What you can do also, if you have questions, I know that some maybe they are not attending, but then after watching the recording, I'll upload the recording on YouTube. Make sure that you go through these problems. If you have a question, you ask. I prefer that questions be asked in the group, but if you don't feel like asking in the group, you can also ask privately. Then make sure that after asking privately, you just tag me in the group and be like, I sent you a question. So because I actually I have a lot of messages, so if you just comment in the group, usually all my messages are mute. So if you comment in the group, I can see that who's asking an academic question, then I can go to your inbox and check. So yeah, then that will be all for now, guys. Thank you for attending. Then I'll share the recording in the group.